Welcome back, everybody. Today we're in section 4.1. We're talking about extreme values on closed intervals. All right, so I want to start by defining something called an absolute maximum. All right, so and an absolute maximum basically says that I have a maximum. So it's a, well, here, I'll just do the definition. Let f be a function with domain D then f has an absolute minimum, absolute maximum, excuse me, at point C if all the other points, all the other y values, are less than or equal to the y value at C. So basically what it's saying is there's an absolute maximum if there is a at the highest possible point in the function. If this is a real number and it's higher than every other point in the function, it's an absolute maximum. All right, for absolute minimum, basically what you would say is if all the other points in the function are greater than or equal to the y value at C, then we would have for all x and d. Then you would have an absolute minimum. A lot of this video is going to be very conceptual. The follow-up to the video is actually in section 4.3, where we'll do it actually more of a computational way of finding maximum and minimum. Right now, I'm hoping that you will just get a feel for the concept. Let's do a quick example. So if I said find the absolute extrema that means absolute max, absolute min, for y equals sine x on the interval negative pi over 2 to pi over 2. And notice it's a closed interval, which means we can land on those. If you have a fairly basic function and a fairly straightforward interval, you can actually just graph it. So if I were to graph this, actually, you know what? That's kind of the wrong way. There we go. That's a lot better. I wanted to get the curve right, but it still doesn't matter. The absolute maximum is right here. Because this is pi over 2. So there's nothing beyond that. This is negative pi over 2. And therefore, you would consider this the absolute minimum. Because on this function, in this interval, there is nothing any lower. Now let's change the function a little bit and see how we do. Next function is y equals cosine x on, and I'll keep the same interval, negative pi over 2 to pi over 2. So let's graph it once again. And what we see is up here is your absolute maximum. And in this case, down here are your minimum. Okay, because they're equal, right? You would say your absolute minimum is negative pi over 2 and pi over 2. And you certainly can check my graph. If you need to, you make a table of values. I've just done these graphs so long that I can do them pretty quickly. Let's take a look at another example. All right, so let's say I don't want to restrict the domain. I just want to know the absolute max, absolute min for y equals x squared. All right, I'm going to draw a quick graph. And remember, it's just a sketch. It's not a drawing a graph exercise, but the graph helps you get a feel for the shape. All right, now both of these go up to infinity. Now the thing to remember is infinity is not a real number. When we're talking about an absolute maximum or absolute minimum, we need a real number. So if you're headed towards infinity, I would say there's no absolute maximum. All right, so no because infinity is not a real number. I know some books may differ, but this is the way we're going to do it. So, and the absolute minimum would be here because the function will go no lower than that. So x equals 0, absolute minimum. All right. But we were talking about restricting on a domain. So how does our answer change? Here we're going to use the same function. If we restrict the domain to 0, 2, but notice 0 is not in my domain. So in this case, this is the way my function looks. Oh, actually, this is gone. And this stops here. Now, this does not go up to infinity now. So where is my absolute maximum? This is my max, my absolute max. And it's x equals 4. Because if I took 2 and I plugged it into x squared, I would get out a 4. All right? So actually that would be y equals 4, but you would, if you say where's the absolute max, say x equals 2. So that's my bad. The minimum would normally be at 0, would be here. However, there is no value for that point. It's not in our domain. But we're getting infinitely close to 0. The trouble is we have no way of showing infinitely close. So for the minimum, the absolute minimum, you would say none, because there's no way to represent infinitely close. All right, let's try one more. Same function, y equals x squared. Let's change the domain to 0, 2, but now it's an open interval. All right, so I'm going to make a quick sketch. Now the absolute min and the absolute max would be at 0 and 2. However, there's open circles there. So you would say no absolute extrema. All right. So, again, this is a very conceptual section. Hang with me. The lesson won't last too long, and 4.3 will be the follow-up on max and min, and it'll give you the real plug and chug type systematic problems. But a certain amount of this is important, so let's take a listen. If f is continuous on a closed interval, then f attains both then f attains both an absolute max and min on that interval. Basically, what this is saying is that if you have an interval that's closed at both ends, so for example, this example here, closed at both ends, here, closed at both ends, you have to have an absolute max and min. Could be at the extremes, in this case, could be in the middle, but as long as the interval's closed, you will have an absolute max or min on that interval. Now here, we had a completely open interval, right? Here we had a partially open interval. And here we had just a generally open interval, all right? Those, you could have an absolute max, you could have an absolute min. You don't have to, though. It's not a requirement. All right. So that is that first theorem. So that's something to look out for. If you have a closed interval, there has to be an answer for absolute max, absolute min. All right. So let's talk about the first derivative. If f has a local max or min, at an interior point, meaning not at the endpoints of the interval, and f prime is defined, then f prime at c has to equal 0. C would then be called your critical number. All right, and a critical number is where you potentially have a max or a min. So if I were to sketch a quick graph, this point up here, where it changes from increasing to decreasing, is also the same exact spot where you have a horizontal tangent line and our slope is equal to 0. So f prime c is equal to 0. All right. So let's try to put this all together. So let's think about the steps we would use. Oop, things got a little haywire. Get out of that. Go here. Okay, good. Steps to find absolute extrema. So the first step would be to find critical points on the interval. Remember, these are all on closed intervals, so we're looking for critical points. The second is evaluate. You're going to take your critical points and your endpoints, and you're going to put them into the original function. I'm going to use CP as an abbreviation for critical point and endpoint. All right, and then whatever y values come out, you take the largest is your absolute max, and your smallest is your absolute minimum. So let's try one computational example and see where we're at. So let's find the extrema of f of x equals 3x to the fourth minus 4x cubed on the interval -1, 2. All right, so first let's find, so the first thing is find the critical points. So f prime of x equals 12x cubed minus 12x squared, and we need to set our derivative equal to 0. Now we need to figure out what x is. So I'm going to factor out a 12x squared, and I'm left with x minus 1 equals 0. So 12x squared equals 0, x equals 0. So I got x equals 0, x equals 1. Now I like using a chart. You don't always have to use a chart, but I like it because it helps me keep my stuff organized. I'm going to say LE is left endpoint. CN is critical number. CN is critical number. Now again, this is just to keep things organized. So, and RE would be right endpoint. So you can write out left endpoint, right endpoint, that's fine. But remember, we're taking our left endpoint, which is -1, and I'm plugging it into my original function. So f of -1, f of 0, f of 1, and f of 2. So at this point, why don't you guys pause the video and scroll up a little bit. Let's see if I can get it in there. So I have the original function up here. Why don't you take those values, plug them into the original function, and let's see what we get. All right. So hopefully you plug them into the function. For f of -1, I got 7. F of 0, I got 0. Then I got -1. And I got 16. So I would label x equals 2 is where our max is. And x equals 1 shows us the location of our minimum. All right. So this would be step 3, and our steps are complete. It just wouldn't be me without stepping it up just a little bit. So let's step it up a notch. I'm going to give you a slightly harder function. 2 sine x minus cosine 2x on the interval (0 to 2 pi). So the first thing we need to do is find our critical values. So what I want you to do is I want you to pause the video. I want you to quickly do the derivative, then come on back and we'll continue from here. Okay, so hopefully you pause the video to work out the derivative. I got 2 cosine x plus 2 sine 2x. All right, so you guys are experts at derivatives at this point, so I'm just giving you the answer. If you did not get that answer, you need to stop and do the derivative right, because going on from here will get you more wrong stuff. All right, so just be careful. Now this right here is really hard to do, okay? But however, sine 2x is a trig identity. It's a double angle identity. You got to look those up. This is one of the reasons why I'm doing this problem. So I have 2 cosine x plus, now the 2 is separate, and 2 sine 2x can be going into 2 sine x cosine x. Now this is important because up here I had x and 2x, and you really can't do much with that. You have to have, if you're having trig functions, you have to have all x's, all 2x's. You can work with that, but you can't have x and 2x. They're not like terms. You really can't do much with it. So this is absolutely necessary here. All right, so make sure that you have those at your disposal. But I'm going to simplify a little bit. I have 2 cosine x plus 4 cosine x sine x, doesn't matter what the order you write them in, equals 0. So now I can factor out a 2 cosine x, and I'm left with 1 plus 2, sine x equals 0. So I have 2 cosine x equals 0, which is basically cosine x equals 0. So x either equals pi over 2 or 3 pi over 2. Scroll up so I can get a little more space. So I have 1 plus 2 sine x equals 0. So then I have 2 sine x equals negative 1. Sine x equals negative 1/2. So x, let me scroll up a little bit more. X equals either 7 pi over 6 or 11 pi over 6. And definitely it's worth it to check my work. All right. If you feel you need to, if you have any questions, definitely come see me. All right. So the last thing you would do is you're going to take each one of those values plus your endpoints. So you're going to take x 0. I'm going to write them in order. Pi over 2. Then 7 pi over 6. 3 pi over 2, 11 pi over 6. And why don't you pause the video now and work on the f of x from the original function. Remember, the original function was up here, right? 2 sine x minus cosine 2x. So you're going to run each one of the x's through that original function, and we'll talk about the answer on the back end. All right, so hopefully you plugged your x's from 0 up to 2 pi back into the original function. Now it's important you plug it into this original function, not the derivative. All right, so up here, this one up here. All right, I did already. Let's see if your answers match mine. I got negative 1, 3, negative 3 halves, negative 1, negative 3 halves, and negative 1. So I would declare this your max. Now I'm going to put it underneath. Those are your minima as well. All right, there's a lot more to do. So I look forward to seeing you next time. Thanks for listening.